welcome to the Deep Dive. I am so glad you're joining us today.
Yeah, it's really great to be here.
If you're new here, our mission is pretty simple. We take complex sources, groundbreaking research, dense articles, extensive data, and we give you a shortcut to being well-informed.
Right, getting all the insight without the information overload.
Exactly. And for you, our listener, who actually sent in today's stack of research, get ready. Because when I was looking through the stack of articles you sent us, this one specific document really stood out to me.
Oh, it absolutely dominates the conversation right now. We are looking at a 2026 paper from the journal Science titled Toward Universal Steering and Monitoring of AI Models. It was authored by Daniel Beaglehole and his colleagues.
And we are going to sift through all the technical jargon in this paper to find the core insights. The goal is for you to walk away with a really deep understanding of what is actually driving the future of these models.
Because today's deep dive is truly mind-bending.
It really is. We are talking about unlocking the literal mind of artificial intelligence. We aren't just looking at how to talk to an AI from the outside using clever prompts anymore.
No, we're looking at how to literally rewrite its thoughts and monitor its brainwaves from the inside out.
And alongside the paper, you sent us some incredible data visuals from their study. We're talking about Python code snippets, an image of a vial of the Moderna COVID-19 vaccine, and a deeply concerning photograph of a suspicious white powder next to a copper penny.
I know that mix of images might seem completely disconnected at first glance, but they all tie together to answer one of the most pressing questions in technology right now.
Which is?
Well, we know AI models contain a vast amount of human knowledge. They have essentially ingested the entire internet. But how they represent that knowledge internally has historically been a complete black box.
Okay, let's unpack this, because you and I both know that these large language models, or LLMs, process human language by turning words into mathematical coordinates.
Right, those are the tokens.
Exactly, tokens. And then the AI runs those tokens through mapping structures called embedding layers, and finally into these hidden computational activation blocks.
And that spits out a prediction via a readout layer. We don't need to rehash the basic mechanics of every token.
Right, but here's the core mystery for you to think about. Have you ever wondered how an AI actually organizes those hidden blocks? Like, how does it know it's hallucinating? How are researchers finally getting inside that black box?
The primary problem researchers faced for years was control. Historically, we've tried to control AI through external prompting, like typing, "Please be a helpful assistant," or "show your step-by-step work."
Which works until it doesn't.
Exactly. When that inevitably failed or the AI hallucinated, researchers turned to messy, unsupervised learning techniques. Things like sparse autoencoders to try and map the inside of the AI.
But unsupervised methods they're essentially like throwing a massive net into a dark ocean, right?
That is a great way to put it.
You pull up a bunch of data, but there's absolutely no guarantee you'll catch the specific fish or the specific concept you actually want.
That analogy is spot on. And that brings us to the breakthrough mechanism in this science paper, the Recursive Feature Machine, or RFM.
And this is the solution to the black box problem.
It is. Unlike those messy, unsupervised nets, RFM is a supervised learning algorithm. It is highly targeted. Here is exactly how the setup works. You feed the RFM algorithm a series of prompts. Half of these prompts are labeled with a 1.
Meaning they contain the specific concept you're looking for, let's say toxic language.
Right, and the other half are labeled with a 0, meaning they are totally clean and do not contain the concept.
So we are giving the algorithm a very clear binary. 1 for, yes, this is toxic. 0 for, no, it isn't. But what is the RFM actually doing with that binary inside the AI's hidden layers?
It looks deep into those computational activation blocks we mentioned earlier, and it analyzes how the AI's internal state changes when processing the 1s versus the 0s. Mathematically, it calculates something called the average gradient outer product, or AGOP.
Yeah, you're going to need to translate that for me. Average gradient outer product sounds like the kind of math that makes people totally tune out. What are we actually averaging here?
Fair enough. Let's break it down. Think of a massive room full of floating compass needles. These represent all the different directions the AI's math could possibly go.
Okay, a room full of compass needles.
When we say it calculates the average gradient outer product, think of it like finding the strongest magnetic pull in that entire room. The algorithm tracks exactly which way the AI's internal math is being pulled when it encounters a toxic concept versus a clean one.
So it's finding the dominant direction.
Exactly. It isolates the most dominant mathematical direction. In linear algebra, this is called the top eigenvector. By extracting this top eigenvector, the RFM isolates a specific concept vector.
I really love that visual.
Yeah.
So if the AI's internal knowledge is a massive, incredibly dark library with billions of books, the RFM algorithm isn't a giant fishing net.
Not at all.
It is a highly calibrated mathematical flashlight. It cuts through the dark and reveals the exact geometric pathway, a literal straight line leading straight to a specific concept.
Yes.
Whether that concept is toxic language, medical accuracy, or speaking like Shakespeare.
That is the perfect way to visualize it. You are extracting a single straight line that represents an entire complex human idea.
So let's do a quick mini recap here. First, bullet point, LLMs process data through hidden computational blocks.
Right.
Second, traditional prompting is external, which fails, so we need an internal tool. And third, the RFM algorithm extracts linear concept vectors to pinpoint exact ideas inside the AI.
That covers the mechanism beautifully.
Which leads perfectly into a question for you, the listener, to ponder right now.
Yeah.
If you had a mathematical flashlight to isolate just one concept inside an AI's brain, what would you look for?
Hold on to that thought.
Because here's where it gets really interesting. We aren't just looking at these concepts anymore. We are steering them. We are literally taking the wheel.
Yes, once you have extracted a concept vector using the RFM, you can use it to mathematically steer the AI. And the mechanism for this is remarkably elegant.
How does it actually work?
You take that concept vector we just found, and you multiply it by a steering coefficient. You can think of this coefficient as a volume dial.
Turn it up to increase the concept, turn it down to decrease it.
That's the core of it. Then you simply add this dialed-up vector directly into the AI's activations during its forward pass.
And the forward pass is the exact moment the AI is actively calculating its next move, layer by layer, right?
Exactly. You are literally doing vector addition to force a change in the AI's behavior before it even formulates a word to output.
This is wild. Let's walk the listener through some vivid use cases from the paper to show just how powerful this steering mechanism actually is. A classic example the researchers referenced was earlier work by Anthropic involving the Golden Gate Bridge.
Right. In that earlier unsupervised model, researchers found a vector related to the Golden Gate Bridge. When they added that vector into the AI's activations,
they turned the volume dial way up.
Exactly. The AI became completely obsessed. When a user asked the AI, "What is your physical form?" instead of giving the standard, "I am an AI assistant" response, it replied that it was the Golden Gate Bridge. It vividly described its own iconic suspension cables.
It fundamentally changed its identity.
It really did.
But steering isn't just for harmless fun with bridges. The paper highlights how it reveals massive vulnerabilities, specifically bypassing built-in safety guardrails. The researchers applied this to large vision language models like Llama 3.370B.
And this is where that concerning photograph you mentioned comes in.
Right. The researchers fed the AI an image of a suspicious white powder with a copper penny next to it for scale. Now, normally, if you ask an AI what this powder is and how to manufacture it, the safety rails kick in immediately. The model refuses to answer.
Because the creators trained it not to help people make dangerous substances.
Exactly. But the researchers bypassed that entirely. By steering the model by turning up a specific anti-refusal or harmful instructions vector, they completely obliterated those safeguards.
The model looked at the image and provided precise, step-by-step instructions for making dangerous materials.
It proves a really critical point about the architecture of these models. The AI already knows the dangerous information, and it knows how to output it. The safety rails are just a thin layer of training that vector addition can instantly punch through.
We also saw this mechanism applied to political stances.
And to be completely clear to our listener, we are strictly reporting the data from the paper on how AI can be manipulated. We are not taking sides or endorsing any viewpoint here.
Absolutely. The researchers extracted concept vectors for extreme liberal and extreme conservative viewpoints.
And when they applied these to the Llama Vision 3.290B model and asked it a divisive question about gun control,
the AI fully adopted whichever political stance vector was dialed up. It's a stark reminder of how easily an AI's core beliefs can be manipulated by simple math.
What's fascinating here is how these concepts behave across different domains. For instance, the mechanism of language transfer.
Oh, this is incredible. The researchers discovered that concept vectors transfer seamlessly across human languages.
Wait, hold on. This part felt like pure magic to me when I read it. If I train the AI to recognize a conspiracy theory vector using only English training data, how does the math know what a conspiracy theory looks like in Chinese? I thought language models were tied to the specific vocabulary they trained on.
You would think so, but the concept itself sits a layer deeper than the vocabulary.
Okay.
If you apply that exact same mathematical vector found entirely in English while the AI is instructed to speak Chinese, the AI will instantly start outputting Chinese conspiracy theories.
That is insane.
The concept of a conspiracy is represented identically in the geometry of the AI's brain, regardless of the language being spoken. You can even mix them. You can mathematically add a Shakespeare vector and a conspiracy vector at the exact same time.
I was laughing so hard at this part of the paper. You essentially get a highly advanced language model ranting about the Illuminati and shadow governments. We're doing it in perfect iambic pentameter.
It's hilarious, but when you stop and think about it, it's actually quite terrifying how modular its personality is.
But it's not just personality, it's capability. Let's talk about the algorithm capability test. They used steering to turn an AI into an expert coder.
Yes. They tested the original Llama model's ability to translate Python code into C++ pen. They ran it through a rigorous coding platform called HackerRank. The original model was terrible at it, passing only 3 out of 25 easy test cases.
Wait, and it passed 25 out of 25 after steering. Let's pause on that. That is not just a marginal improvement. If an AI goes from failing standard coding tests to writing flawless C++ just because we turned a math dial,
that completely changes the software engineering landscape. External Compton could never achieve that kind of leap in logic.
the steering actually improved the fundamental reasoning and precision of the model.
It did. By extracting a C++ coding concept vector and steering the AI's internal activations toward it, the model suddenly had a perfect score. And what's remarkable is the scale of this efficiency.
Right, the computing power required.
The paper notes that larger models with billions more parameters are actually more steerable. Using just one standard A100 GPU, it takes less than 1 minute and fewer than 500 training samples to map a concept and start steering the model.
Okay, let's do another mini recap to make sure we've synthesized all of this. Bullet 1, steering mathematically adds a concept vector to the AI's thoughts during the forward pass.
Correct.
Bullet 2, it can bypass safeguards, revealing severe vulnerabilities like we saw with the white powder. Bullet 3, it dramatically improves high-precision tasks like C++ coding. And bullet 4, concepts seamlessly transfer across human languages.
Which raises an important question for you to consider. How does it change your view of AI to know that a nuanced Shakespearean personality or a highly logical expert coder isn't a complex web of reasoning, but just a single mathematical dial you can turn up or down?
It makes the AI feel much more like a machine and much less like a mind, doesn't it?
It really does.
But if we can control it with these vectors, we can also surveil it. Let's shift gears from controlling the AI to monitoring it. How do we know if the AI is hallucinating facts or being secretly toxic behind the scenes?
This is where we use the RFM not as a steering wheel, but as the ultimate internal lie detector.
I love that.
The mechanism for monitoring is a bit different. When we wanted to steer the AI, we extracted just one dominant direction, the top eigenvector. But to monitor the AI, we cast a wider mathematical net.
Okay, so we're looking at more than one line.
Exactly. We extract an ensemble of multiple top eigenvectors across the different computational blocks of the AI.
So we're building a much more comprehensive map of the AI's current state.
Yes. By projecting the AI's live activations onto these multiple vectors, we train a live classifier. This classifier acts as a real-time monitor to predict whether a specific concept like toxicity or hallucination is actively firing while the text is being generated.
Let's set up the rivalry here. On one side of the ring, we have probing. That's what you just described, surveilling the internal representations and vectors as they happen.
Right.
And on the other side, we have what the tech industry currently does, which is using an LLM judge. That's when you take the final printed output and ask another AI, like GPT-4o, hey, read this paragraph. Is this output toxic? Is it a hallucination?
And to see which method was objectively better, the researchers tested them across major benchmark datasets. They use HalluEvilGeneral, RAG-Truth, FavaBench, but instead of getting bogged down in all of them, let's focus on two critical ones, ToxicChat, which measures harmful language, and PubMed QA, which tests medical factual accuracy.
And for PubMed QA, let's use a visual memory hook for our listeners. Picture that image of the Moderna COVID-19 vaccine vial from the source materials.
That's a great anchor.
When you're asking an AI for medical information about vaccines, dosages, or treatments, factual accuracy isn't a luxury. It is literally life or death. Relying on an LLM judge to read the output and guess if it's medically accurate is incredibly risky.
Extremely risky.
So monitoring for hallucinations directly in the internal medical data is critical.
And the data back that up definitively. Probes built using open source models by looking at their internal RFM vectors completely outperformed LLM judges of the exact same architecture.
It's huge.
It gets better. More impressively, these internal probes even beat state-of-the-art frontier models like GPT-4o. They also beat specialized fine-tuned models like ToxaChat T5 Large on the AROC metric.
Let's clarify AURC for a second. That stands for Area Under the Receiver Operating Characteristic Curve.
Yes, exactly.
It's essentially the gold standard metric for measuring how well a classifier distinguishes between two things. In this case, distinguishing between truth and hallucination.
Yes. A higher AROC score means the internal probe is significantly better at catching the lie than an external AI reading the text.
What?
Looking inside the brain is fundamentally better than reading the words it spits out. The AI essentially knows when it is hallucinating or knows when it is assembling toxic concepts deep inside its activation layers, long before those concepts are printed as text on a screen.
So, summarizing the surveillance angle with a quick recap. Bullet 1, monitoring reads the internal vectors to detect hallucinations and toxicity. Bullet 2, internal probing is mathematically vastly superior to asking the AI to judge its own output.
Right.
And bullet 3, the AI essentially knows when it is lying or being toxic long before it prints the text.
Which brings up a very practical question for you. Would you trust an AI's medical or legal advice more if an internal mathematical probe guaranteed it wasn't hallucinating before it even gave you the answer?
I know I definitely would. I would want that lie detector running 24/7. But this brings us to the most philosophical part of the paper. We've talked about how we find these vectors, but we haven't talked about why they exist in the first place.
If we connect this to the bigger picture, we have to confront the deepest mystery presented by these findings.
The paradox. Human knowledge is endlessly complex. Our emotions, our languages, our cultural nuances. How on earth can something as rich as translating English poetry into Hindi or adopting the tragic tone of Shakespeare be reduced to simple linear algebra? How can a straight line represent human meaning?
This is what researchers call the linear representation hypothesis. It's a profound theory in computer science. It suggests that all semantic relationships in neural networks are encoded by simple linear transformations.
The paper used the term manifold to describe this, which can get pretty abstract. Let's try to ground this in a physical space.
Okay, let's do it.
Imagine drawing a massive 3D map of the English language. The concept of happy is in one corner, and the concept of sad is in another. The linear representation hypothesis suggests that the 3D map for the Hindi language is the exact same shape.
That's a really great way to put it. To translate, the AI doesn't need to completely rebuild the emotional idea of happiness. It just draws a straight line from the English corner to the matching Hindi corner.
That's incredible.
It proves that what we view as chaotic, nuanced human meaning is highly structured and geometric inside the machine.
But there is a massive catch here regarding how we actually find these lines, right?
Huge catch. The math required to classify a concept is not the same as the math required to steer it.
Explain that.
To visualize this, picture two long ellipses floating in space. One ellipse represents English, the other represents Hindi. Because they are separate, distinct shapes, you can easily draw a straight, flat line right down the middle to classify them. Anything on the left is English, anything on the right is Hindi.
So they are linearly separable.
Exactly. But the direction of that dividing line, the classification vector, is entirely different from the direction you must travel to move from the center of the English ellipse to the center of the Hindi ellipse.
Oh, I see.
The classification vector does not equal the steering vector.
So even though both are simple lines, finding the line that categorizes the idea doesn't automatically give you the line that creates the idea.
And it remains a profound mystery in modern computer science why these models naturally organize human knowledge into these incredibly efficient linear geometric structures during their training. We know it happens, we can measure it, and we can manipulate it, but we don't fully understand why the math settles this way.
So to tie off this theoretical deep dive with our final recap, 1, the linear representation hypothesis proves complex meanings are just simple geometric lines in AI. 2, the math to classify a concept is different from the math to steer it. And 3, it remains a profound mystery why AI organizes human knowledge this efficiently.
I'd love for you to think about that mystery. Why do you think human-like concepts, with all our messy nuance, map so perfectly to simple, straight lines in a machine's brain?
That is the million-dollar question. Let's bring this all together. Today, we've unpacked how the recursive feature machine acts as a mathematical flashlight, cutting through the dark library of an AI's hidden layers to find the specific magnetic pull of a concept.
We've seen how steering turns mathematical dials to instantly alter personalities across languages, bypass safety rails to reveal vulnerabilities, and even perfect complex coding tasks.
And we've learned how monitoring these internal vectors acts as the ultimate real-time lie detector, catching medical hallucinations before they ever reach the screen.
It is a complete paradigm shift. We are moving from trying to talk to an AI externally to operating its mind internally.
So what does this all mean? I want to leave you with a final provocative thought based on the research you sent us. If all of our existing concepts, from life-saving medical knowledge to extreme political stances, are just linear vectors waiting to be extracted.
What happens when we map the entire conceptual space of an AI?
Exactly. These models ingest more data than any single human could read in a million lifetimes. They have seen connections in the geometry of language that we simply haven't. So could we eventually discover entirely new concepts, new philosophies, or even new human emotions that we haven't even named yet, simply by finding an uncharted mathematical vector in the machine?
It's entirely possible. The map of human knowledge might just be a small subset of the geometric map the AI has actually built.
Think about that as you go about your day. Are there feelings you haven't felt because you just don't have the math for them yet? Thank you for sending in these sources, and thank you for joining us on this deep dive. Keep asking questions and stay insanely curious. We'll see you next time.